And hello. So in the previous video, I would put the link in the description, and then you can also see it at the top right corner of the video screen. I hope it's the top right corner. Yes, I think it is. Yeah. So in the previous video, we calculated the Lorentz force detuning on the Tesla cavity, and in this video, we would calculate the pressure sensitivity on the Tesla cavity. So I've already gone ahead to kind of do some preparation just like in the previous video. So just to brush over it, I started from the Tesla cavity. Don't mind the grid stuff, it's a face. I think I could also maybe turn, no need. So I started from this, which is set up for ideal mode simulation, and this is vacuum, and then shelled my cavity already and applied, so it's shelled, and applied the niobium as the material of the cavity wall. So and then also set the thickness to, I think it's 2.5 millimeters, as was recorded in this paper, which I would also, so this paper, the paper also referencing the last one, I would also put the link in the description. So yeah, I think this video will be short because it's not much different from what we did in the previous tutorial. So I'll just go ahead and apply my boundary conditions, which is the same as last time. Now just to note, your results greatly depend on your boundary condition, and I'll be doing a video, so applying a boundary condition, so I'm fixing this end and also fixing this other end. I'll do a video in the future that has a kind of varying stiffness at the boundary, so you see how the deformation varies with the stiffness of the at the ends of the cavity. So that's now for the Lorentz force detuning. At this point, we went ahead to import the Lorentz force from the eigenmode analysis, but then we are not doing that today. We want to calculate the um, pressure sensitivity. Now, where does the pressure come from? So the cavity is typically contained inside a cryomodule. Okay, superconducting cavities is contained inside the cryomodule for cooling, and then you have the helium surrounding it. Now inside of the cavity is maintained at a vacuum, but then the external helium provides applies a pressure to the walls, kind of bending it, trying to bend it in, and then you can also see that in this paper. So yeah, it is also helium pressure variations lead to changes in the resonance frequency, and I think this was measured for an actual cavity as shown in this figure. So I think this was measured for actual cavity. So you have the detuning depending on the variation in helium pressure over time. So and yes, so we are going to apply that pressure to the surface of the cavity wall, and for that you go to the traction boundary condition, and then you select the faces. Okay, this is yes, and so we go from Cartesian to normal, and so this is normal to the faces. So I think that the normal is pointing outwards of the face, so I'm going to apply 1 bar to the opposite, so the opposite of the normal. So I'm using minus 1e to minus 4. So 1e to minus 4 gigapascal is equivalent to, sorry, is equivalent to 1 bar. So I apply that, and yeah, that's it for the analysis. And then I go to setup. Now in the Lorentz force detuning video, we could click on settings because we imported field, and then we could apply factor. I'm not going to do any adaptive mesh refinement because this is just a demonstration, and I'm not really bothered about the accuracy of the results. Now you could also go into specials, and then you could turn on gravity, but again this is just to show. I'm not going to turn on gravity because I'm only interested in how this how much sensitive this is to pressure. Now you could also consider large deformations, and this is when you have large deformations in your model. I do not expect any large deformation in this model. Your pressure is 1 bar, so it's not that large. But then if you use a large pressure, then you might consider it. But then for this simulation, there's really no need to use a large pressure, because in the end we are still going to divide out. So yes, but then if you should go to the help page, then you see an explanation of cases that you need. So you go to non-linear mechanical solver that you need non-linear model for. So you see that kind of this bar, if you had linear model, then you had this behavior which is clearly not correct, and then you have also the deformation, the maximum deformation, which is different when you apply this, and then this is the more accurate model. So for large deformations, take care to um, turn this on, so consider large deformations, and then you could also play around with these settings. So but we do not need it for this, and yeah, you could also select your solver type again. We'll leave it as automatic. So yes, and I'll start the simulation and pause the video and come back when it's done, because I think it takes about 2 minutes. Okay, the simulation is done and we can go ahead and view the results. So you could view the displacement if this would show up. So I have a CST problem. For some reasons my fields are not okay. You have different misses, but then like in the last tutorial, and then it just goes blank. So you have this, but then it's almost always with the displacement, it almost never shows. So I think I could look at this and then but then like before, you could, this doesn't work, you could scale it and then see. I wish it would even appear just once. How do I get it to appear just once? Displacement. I think this is a CST problem, and I think I have to update as soon as possible. So yeah, it's okay. Even sometimes it doesn't show the other ones. Yeah, oh yeah, for a split second there you could see it. Maybe you could pause and see it, and then you also had the, yes, displacement. Crazy. If I should go to this, and then I could see the phone misses and then come back, then okay, it doesn't show again. But yeah, I think you already saw it in the last video. You could put a factor and then see how it's deformed, so you could increase the scale of deformation. So we have a maximum deformation of 0.0279 millimeters. So to calculate the sensitivity, this field is exported to your ID mode analysis, which I've also gone ahead and set up. And if this would save, and okay, so I already created this and I already ran the simulation, but then I would delete the results. Oh, crazy me. And so already went ahead to set up my, oh, something I forgot to mention. Now in the last video, I forgot to turn the background to normal. So if yeah, just to mention it in the last video, which is the Lorentz position, I don't know if I mentioned it again, but then I forgot to change the background material to normal. It was still PEC. So just to mention that. Now for the ID mode simulation, I had gone ahead and set up my frequency minimum or maximum, then the background, change it back to PEC. So this is vacuum, so solid, not with niobium or anything. So, and then the boundaries, yeah, also set. So now the only thing I need to do is to import the field, and then inside this project, because I created everything as a project, inside of this project I have these files where I could import. I mean, I could select anyone, but then if there's no field, okay, they have different fields here, but what I need is the displacement field from the pressure sensitivity. Now if this if I didn't run it in a project and I wanted to import the displacement field from an external project, then I would click on select and then navigate to the project. But for this, I go to pressure sensitivity and I need the displacement field, and okay, and that's all. Then make sure you check use sensitivity analysis, because here you have that field 1 is already checked automatically for sensitivity analysis. So I click OK, and I would run this simulation again, and yeah, I'll pause the video and come back when it's done. And the results are in again. So from the messages you could already see yeah, sensitivity values and frequency shift values. So which mode are we interested in? I think it was mode 7. Yes, mode 7 is accelerating mode. Yes. So we go to 1D results, and then sensitivities, and then mode frequencies and field. Then we click on mode 7. So what we have, I mean, we could also check for other modes, but we're not interested. So what we have is minus 0.0049 something. So on this paper, you have that, I mean, sensitivity is given in 10 in hertz per millibar. So first of all, let's convert this to hertz per millibar. So currently it's this megahertz. So I just go to calculator and then type in 0.00495 e to power 6, then divided by 1e3. So I use 1 bar for the simulation, for the mechanical analysis. So converting to millibar would be, yeah, multiplying by 1 to minus 1 to 3. So calculating this, I have that my sensitivity is 4.95 hertz per millibar. So let's see what they have in the paper. The paper, they have something different, which is 10 hertz per millibar. Now I think this was done by measurement of the actual device and the setup. So the stiffness, of course, it's not fixed at both ends, so it has like some um, flexibility. There's actually another term for it, but then it's free to move at both ends, even though it's small. So so I think that is the reason why there's so much discrepancy. I mean, from the simulation with fixed ends is 5 hertz per millibar, and then on the paper, the actual model, it's 10 hertz per millibar. But then this was just to show the process of how you could do it. In a future video, I'll be carrying out analysis with different stiffness of the boundaries. So you see how much the displacement and also the frequency shift varies with different stiffness of the boundaries at the boundaries. So yeah, I think that's it for this video. I hope I did not miss anything. I doubt. And yes, I would also link the paper in the description. I think I already said that. So yeah, till next time.